Okay, let's analyze this problem using tangential and normal components for acceleration. So we got an Amazon conveyor moves boxes along at an acceleration of 0.2 t meters per second squared. If the box starts at rest at point A, which is here, at what's the acceleration at B? So for our acceleration, we have tangential component plus a normal component. So let's begin here with our tangential component. And AT at B. So again, this equals dv dt of 0.2 t meters per second squared. So the integral of a dt from 0 to t equals our integral of dv from 0 to whatever our velocity is, v. So this is going to be the integral from 0 to t of, let's stick in our equation, 0.2 t dt. So we end up with 0.2 over 2 t squared equals v minus 0, or v. So this is 0.1 t squared. Let's go ahead and underline that. So what was the point of this? The reason is because with our tangential acceleration, our first component here, we want to figure out what t is. And an equation for this is given. Actually, up here I should have called this a sub t. So that's why I derived the velocity in terms of t, because I can now then take this, and we have more information here in terms of the path s, because we have all these dimensions up here on our conveyor belt. So ds dt equals v, and again we just derived this equal to be t squared. So let's do this integration now, and let's integrate ds from 0, our start, along the length 3 meters plus a quarter of a circle here. So s equals essentially 3 plus pi pi r times 2 for the circumference of a circle, and then we're only interested in a quarter of that, so divide that by 4, and this whole thing ends up equaling 6.142. And then set this equal to the integral of, from velocity starts at 0 according to our problem, our time starts at 0 to time t that we're trying to figure out, 0.1 t squared for velocity dt. So this is v dt. Okay, solving these integrals, we get 6.142 equals 0.1 over 3 t cubed, and then it's just a simple matter of solving for t. So t to get to b essentially equals 5.690 seconds. Okay, so then we can figure out what our tangential acceleration is. So our tangential acceleration at 5.69 equals 0.2 times 5.69 according to our given function, and that equals 1.138 meters per second squared. Again, that's our tangential. And since that's one piece of our solution, we'll box it. Okay, so now it's just a matter of plugging and chugging for our acceleration in the normal direction, and that equals b squared over the radius, which is essentially looking at that at 5.69 again. We'll just put in the equation we derived, 0.1 t squared, 5.69 over the radius of 2, and this equals 5.242 meters per second. Okay, so our acceleration then is 1.138 meters per second squared plus, and this is in the tangent direction, plus 5.242 meters per second squared in the normal direction. So then that is our magnitude of our acceleration. Okay, let's try this problem now. When a skier reaches A, he has been on a parabolic path for the last couple seconds with a speed of 6 meters per second, increasing at 2 meters per second squared. Find the direction of his velocity and magnitude and direction of acceleration at this point. So this curve is a parabola, y equals 1 over 20x squared. So we have x, or y, as a function of x. Now we can define, obviously, a tangent here and a normal. Let's put these as unit vectors. U tangent and a U normal here. Finally, we want a distance of 10 meters to this point, and in the vertical direction, 5 meters. So we know our velocity is tangent to the defined y as a function of x curve. So let's just find a tangent to that curve. We already have the magnitude. So a tangent, so the slope essentially is dy dx, which is the derivative with respect to x of 1 over 20x squared. So we're looking at 2 over 20x equals x over 10. So since our position of x is 10, our slope at 10 equals 10 over 10, which is 1. So our rise over run is 1. That means that essentially the tangent, the arctangent of 1 equals 45 degrees, which makes sense. And yeah, here we go. Boxing our velocity 6 meters per second at 45 degrees, since that is the arctangent of 1. Okay, so our acceleration is our tangential acceleration plus our normal acceleration. And this first term is given as 2 meters per second squared. So we just need to figure out the second term. The velocity actually is given v over r squared. So this is 6 meters per second over r, or rho squared, or v squared over r. My mistake. And that's in the normal direction. So we just got to figure out what r is. And then recall that our rho, or radius of curvature, is this relationship. We can go ahead and solve that relationship for our coordinates that we have. So setting this up, the derivative of y with respect to x is 1/10 x. Not squared, but just 1/10 x. And the quantity squared, raised to the power of 2/3, divided by the second derivative of this. So the derivative of this is just 1/10. And we want to solve this when rho equals 10, because x equals 10 at this point, given in our problem. That then, plugging that in, you're going to end up with 28.28 meters as radius of curvature, which means we can now go and solve for A. And we've got 2 meters per second squared in the tangential direction, plus 6 over 28.28. This is actually going to be 36 because it's v squared. Let's put parentheses there. 36 over 28 u sub n. So we can do that math, simple math, and then we can figure out what our magnitude is, because that's what the problem asks for. So this is going to be 4, which is 2 times 2, and 1.273 squared. And that equals 2.37 meters per second squared. Equals A. And I don't have my nice, neat making a rectangle on. So then we just got to find the angle here. Okay, so for the direction, we know that the tangent is at 45 degrees. We found that earlier. That means our normal is 90 degrees from this, and our, essentially our acceleration is somewhere like this. Let's call this a phi, and that equals the arctangent of the tangential over normal acceleration, which is 57.5 degrees. Then we can find this smaller angle theta, which equals 12.5 degrees. And then here's our result.